name is Abdelrahman and today I'll be presenting about internal forces. Internal loadings developed in structural members. Beam. It's a structural member designed to support loads applied at various points along its length. Beam can be subjected to concentrated loads or distributed loads or a combination of both. Beam design is a two-step process. Determine shearing forces and bending moments produced by applied loads. Select cross-section best suited to resist shearing forces and bending moments, as shown in Figure A with concentrated load and Figure B with a distributed load. The internal loadings can be determined by using the methods of section. The normal force MB acts perpendicular to the cross-section. The shear force VB is tangent to the cross-section. The moment MB is the bending moment at the cross-section, as shown in Figure A and B. Internal loadings developed in structural members. The internal forces can be determined by applying the equations of equilibrium to the FBD or free body diagram. A direct solution for normal force MB is obtained by applying sigma Fx equals 0. Shear force VB is obtained from sigma Fy equals 0. The bending moment MB can be obtained from sigma MB equal 0. Sign convention. Normal force is positive if it creates tension. Shear force is positive if it causes beam segment to rotate clockwise. Bending moment is positive if it tends to bend the segment in a concave upward, as shown in the three examples I have provided to you, seen on the right. Procedure for analysis. Draw FBD, all the external forces and support reactions. Before the member's section, determine its support reaction. Pass an imaginary section through the member perpendicular to its axis and indicate all internal forces. Apply the equations of equilibrium to determine the internal forces. Shear and moment equations and diagrams. The variations of shear force and bending moment along the beam's axis can be obtained by using the method of sections. Shear and moment functions are discontinuous. Slope changes where concentrate forces or concentrate moments are applied, as you can see again in the three figures I have provided for you on the right. As you can see in this example, this is the use of the formula of V equal W capital L divided by 2 minus WX equal W multiplied by capital L divided by 2 minus X. For M, it's equal, the formula is equal W divided by 2 multiplied by capital L multiplied by X minus X squared. So to get the M of, or the max M, it equals W capital L squared divided by 8. And as you can see visually on the figures on the left. So let's take an example. Determine the internal force, shear force, and moment at point C. As you can see, the beam here and the points are clearly shown as point C is in the middle. So the answer for this is you have to first start by getting the moment at point A, which must equal 0. So By, so the force of Y, or we don't know on point B, multiplied by 6, the distance, minus 10 multiplied by 1.5 minus 15 multiplied by 4.5, which equals to 0. This results in By equaling 13.75 kilonewtons. Since there is no any force on the x-axis, it equals to 0. To get the sigma Fy, we must equate it to 0. So Vc plus 13.75, which we got from the moment, minus 15 equals 0, resulting in Vc equaling 1.25 kilonewtons. These are the two answers we want, the sigma Fx and the sigma Fy. Determine the normal force, shear force, and moment at point D. As you can see in the figure here, point D is in the mid of pin C. As you can see, this is the answer for it. Support reactions. Notice that member AB is a two-force member referring to the FBD of member BC. So first let's start by getting the moment of point C. So FAB, which is unknown, multiplied by 1.5, the distance, minus 900 minus 100 multiplied by 4 equals 0, resulting in FAP equaling 867 newtons. Let's look for the sigma Fx, which we must equate to 0. So Cx minus 867 equals 0, resulting in Cx equaling 867 newtons. Sigma Fy equals 0. Cy minus 100 equals 0. Cy thus results in 100 newtons. Internal loadings, referring to the left segment of member AB section through E in the figure, sigma Fx must be equal to 0, so Ne minus 867 equals 0, resulting in Ne equaling 867 newtons. That is the first part of the answer. Sigma Fy equals 0, but there is no y force on the y-axis, so it's 0. The same with the moment. There is no moment on point E, resulting in it being equaling to 0. Referring to the left segment of member BC section through D, sigma Fx must be equated to 0, so Np plus 867 equals 0, so Np is 867 newtons, which is the answer we need. Sigma Fy equals 0. 100 minus Vp equals 0. Vp equals 100 newtons. The moment of point P, MP is, or B, I'm sorry, B minus 100 multiplied by 2 equals 0. MD is 200 Newton meter. That is the answer we need, or the moment of point D. As you can see in the free body diagrams provided below, this made the question much easier to draw the free body diagram and do the method of section to get the final answer, or the multiple answers we need to determine the normal force, shear force, and moment at point D. Draw shear force and bending moment diagram for the following beams. As you can see, there's no numbers. It's up to us to provide all the shear force and bending moment diagrams. So as you can see here, for 0 is less than x, or less than or equal to x, which is less than a, sigma Fy equals 0, so V equal P. Moment of sigma moment equals 0, so moment is P multiplied by x. For a is less than x, less than L minus a, sigma Fy equals 0, so V equals 0. Moment equals 0, so negative px plus p multiplied by x minus a plus m equals 0, resulting in m equals pa. For L minus a, less than x, less than or equal to L, sigma Fy equals 0, V equal negative p. The moment of m, which must be equal to 0, is negative m plus p multiplied by L minus x equals 0, m equals p L minus x. As you can see, also given in a more visionary matter, or a more visual matter, the diagrams you can see on the right providing the shear and bending moments for the following beam. I hope this video helped to understand the internal loadings section, and thank you very much, and I hope to see you next time.